Hello, I'm Chris Athanas. This mic's in the way. I'm a KMP developer, and we're going to be doing the next episode in this series, how to program from the ground up. And we're going to get into the hardware, which is the fun part. I like it. I like hardware. I think hardware is cool. I think it's fun. So you can go download this document in the description below, and then I'm going to read it on the web because it's a little nicer on the web. So let's get into hardware. And here we go. So hardware, we gotta have a machine to do our work. We can't do it ourselves. I mean, the abacus is kind of like the machines like those. Clay is sort of considered. I don't know. Abacus is probably the first kind of machinery because it's moving things where we touch and move around. So until we all attain accurate psychic powers, there must be some kind of mechanical or electronic device to do the work for us. All right. So low-level hardware implementations. This is the most basic thing that you have is the wire and the battery. And that started in the 1800s when they started doing these experiments. And the big idea is a wire can be used to represent a Boolean logic state. I'm not talking about the Boolean logic. Once we have the and or not, we can do computers of any type. And we'll get to the types. So all the hardware types we've come up with so far. So is there electricity flowing or not? That's the big idea of the state. Is it state? Is it not or not? And that could be represent a Boolean state, logical ones, zeros, connected or not connected. And the problem is we don't really know the state of a wire connected to a battery until we measure it somehow. Like either we feel it with our fingers if it's hot or not. A totally legit way of doing it. I've used that one quite a bit to see if something's current has been flowing to something or not. Or you can see it smoke. Smoke. And that was probably the origins. Like when they were heating these wires, they would glow white hot. And that's basically what a light bulb is. It's just a little wire inside a vacuum.
Like this light up. You need to have current
glowing white hot.
Glowing
white hot and not burning. Right? That's why the vacuum's there, because there's no oxygen, so it doesn't burn. So that's why it can glow for so long.
Bulb like this light up. You need to have current coming into the nub part right there and then coming out of the side, or it doesn't matter, it goes either way.
Yeah, it's connected
and then that makes this filament with electric current runs where it get really hot and glow. That's how these incandescent bulbs work. So here's this. It's kind of hard to do with one hand, but I can do it anyway. So here is a wire. I only need one. You only need one wire. I'm going to put the battery on top of that. It's hard to do with, like I said, with one hand, with two hands even. Now I'm going to put the side of this on that, and I'm going to touch this to the nub. I don't know if it's actually called a nub. But let's see if you can see that light up. And it doesn't work. There we go. And try it on this side. So in this case, I have a complete circuit.
That's it. That's the simplest thing you can kind of get into is that type of circuit. So I gotta do that. So a simple switch with light. So when the thing's unconnected, it's like acting like this little switch. That's all a switch does is it breaks the connection in that current. So the big idea can be, instead of touching with our fingers or trying to put it all together with your hands, they make a little switch so you have a little button to press now and a mechanical device. And all it's doing inside is that same thing, putting the wire together. That's it. So they adds a visual feedback, whether we know what the current circuit is actually connected or not, without having to feel it or touch it or use a voltmeter or whatever, is the light. You can see the current flowing through the current electrical current flowing through this electrical connection here, glowing white hot. That's what we see. It's incandescent. Okay, giving off electrons and photons. All right. Okay, so that was basically Boolean gate. When it's off, it's 0 or false. When it's on, it's 1 or true. That's it. And an AND gate. Okay, so we got the OR. Let's do the OR first. Oh no, we'll do the AND first. So if you have two of these in series, right? If two of these little things in series, one switch and then one other switch after the other, you get an AND gate. So if both, and they call it a gate because it's like walking on a path, right? In this case, the gate is closed even though the circuit is open. They call it, it's not confusing, right? The circuit is considered open here. The circuit gets closed when the switch gets closed, which is like having a path through a gate that's now open. I know it flips it back and forth. And there's a lot of stuff in this field where they are mixing these metaphors back and forth. We have a closed circuit is the same as a gate that's open. That allows things to pass through. So that would have been one of the sources of confusion, because these mixing of metaphors happens quite a bit in this field, as we'll get into very shortly. So if both gates are closed, you're not going through. If one gate is closed with the other, you're not going through. If this gate's open and the other one's closed, you're not going through. Both gates have to be open to go through, or both gates. The circuit has to be closed for it to be closed here, and the light to show up to shine. And here we have the OR. So the OR just instead of doing in series, there's in parallel. So just another. You can go this way or go this way with the OR gate, and then let's go ahead and. So you take one or the other. If either one of them goes, you're going through. If either one of the gates are open, you're going through. Either one of the circuits is closed, with the switches are down. The switches are closing the circuit. Either one, it's going to make the light come on. Yeah, that is it. That is the big idea. Ooh, big idea. Ooh, Boolean logic.
Presented by Cal.
So this is another way of thinking about these water gates. All right, let's check out. And there have been actually computers made out of these water gates like this. Full computers. Great. You can see
information is a disembodied thing. It's bits. We're told it doesn't matter what form the bits take. They can be radio signals, they can be scratches on a piece of paper, they can be little magnetic regions on a magnetic disc, they can be little scratches on a CD. So somehow, in order to process information, we have to give it a physical form. When you put electrons in a conductor, like a wire or a piece of silicon, they actually act a lot like a fluid. They're not little pellets of charge rattling around. They act like a fluid. And the fluid that most of us are most familiar with is water. And we're going to talk about how you use a fluid to give information a physical form. We have a source of water up here. It's a little trough that runs along. That's the source of the water we're going to use to process our information. And here's a valve that will allow that water to go into this tank.
Or a gate. You can also consider this a gate where, someone's walking in through this path and the gate is closed, so they can't go through. That's another metaphor they use in this. And so this guy, Carver Mead, which is crazy, only has 831 subscribers, because this is the guy that actually created the VLSI chips, the very small, tiny things that actually made microprocessors or microcomputers actually possible. He made the first public one. Of course, DoD had it. Who knows how long before that, like at least 5 years. Maybe 3, who knows. Anyway, it was secret for a long time. Interesting story.
Where we store the water. And here's a valve that has been opened so it's drained all the water out of the tank. And this arrow here indicates that the valves are connected in such a way that when we change one of them, we change the other one too. So when this one's open, the bottom one is closed, and vice versa. We're going to make a physical bit. So here's a digital bit. It's a logical 1.
So it means that the tank is full, it's a 1, okay.
Tank full of water, with the upper valve open and the lower valve closed. And then we switch the valves. We close the upper one and open the bottom one, and all the water drained out of the tank. And now we're representing a logical 0. We've
That's it.
made a logical transition. So just from this much already, we can say a lot about information processing in a physical form. The first is we need a supply and a place to get rid of the medium, in this case the water. Up here we have this trough, and down below we have some kind of gutter where the water can get away. Otherwise we can't change the state. Well, we don't want to waste all that water, so there has to be a pump someplace that pumps the water we've used back up into the trough. That pump is called a power supply. And it takes energy. The water up here in the trough is at a higher level than the water in the gutter that we're finished with. So it takes energy to pump that water down below up above, where it can now be used to process more digital 1s. And every time we make a transition between a 1 and a 0, or between a 0 and a 1, we lose energy. We lose the energy of the water in the trough when we fill the tank with it, and we lose the energy of the water in the tank when we let it out into the gutter. So it takes energy to make a transition between a logical 1 and a logical 0. And it takes time. The valve can only pass so much water in a unit time. So to fill the tank, it's going to take time.
And this tank is like a relay on a memory. If you're using relays to store batteries and stuff, how long it takes to close the relay or open it back up again. And the tubes, how long it takes for the electrons to slow down and stop. If, when the gate is closed, how long does it take to stop versus how long does it take to start again? This is all throughout. This is what the clock speeds. That's why things had to get really tiny to get super fast, because you only need to fill up a tiny little amount and then drain it out a tiny little amount. But the water analogy holds up. This could be electrical charge. It could be water. It could be relays closing, opening. It could be all kinds of stuff. Photons on a thing, whether they get to decay away or they stay available. Mm-hmm.
And the bigger the tank is, the more time it's going to take to fill it, unless we get a bigger valve. If we're going to transport the information in one of these tanks to be used somewhere else, we need to run a pipe over there. And when we fill this tank, we have to fill that pipe too. So when we distribute information, it costs time because it'll be more water we have to run through the valve, and it costs energy because that water costs energy to fill the tank or to empty it. So we've learned a lot already about time and energy use when we process information.
And those pipes can also be the wires. You know, that's the analogy. It holds up.
And that's as true of silicon as it is of water. Now suppose for a moment that we take this tank that's storing our digital 1, and we arrange the valves in such a way that they don't turn at the same time. Well, one thing we can do, it's a very important thing, is we can leave the bottom valve closed, but we can close the top one too. Then we end up in this situation here. Here's a tank full of water. Can't take more water in, can't let any water out. Then we can take the power supply away, that trough that supplies the water, and this bit will stay in the tank. So we have a mechanism of memory. That memory mechanism is exactly what is used in what are called dynamic random access memories. They're in all your cell phones and all of your computers. Exactly that mechanism.
Yeah, those are using capacitors. It's exactly how it works.
Next thing we need in order to process information is to do logic functions. This is an example of a very simple logic function. I have a tank here which I filled through this valve. So that's a logical one. I can also fill the tank through the other valve. So if this valve on the right is allowing water in, or if the valve on the left is allowing water in, I get a 1.
Yeah, so this is this table here. The or. Where is it? Yeah, here. Yeah, or. This one. That's what he's talking about. This is the one side on the left side, the A. This is the B. This is the result. And yeah. And this is the reset here if you want to get real technical.
For the output. But if neither the right-hand valve on the top or the left-hand valve on the top is open, I get a 0 for the output. When you have a representation for the bits in physical form, where you have a mechanism of storing that representation of a 0 or a 1, and when you can combine that representation of 2 or more bits to make a new result, that's all you need to do universal computation.
That's all you need. If we have a way to, instead of using the silicon chips and electricity, we find some other way of doing it with this type of thing, we can do the same kind of stuff using that new medium. It's like flashing lasers into xenon gas arrangement. It does it better, then we're all going to become X-ray techs.
So we've seen that the important thing that happens for storing, for remembering, and for computing new bits are the operation of these valves. In order to do anything useful, the setting of those valves has to be able to depend on the water in another tank somewhere. So it has to be the water in the tank that sets the valve on some other tank.
Or the electrical battery, or where you plug it into the wall, it's being generated at a power station somewhere. That electricity, that's how it drives this whole thing, is that electricity. So a water source somewhere, or it's electrical, same stuff.
That's what we need to get computing done. The pressure in this tank, which comes from how high the tank is filled, the higher it is, the more pressure there is down here at the bottom. That pressure, when it's electrons, is called the voltage. So what we're asking is an electronic device that will turn on or off, allow electrons to go through or not, depending on a voltage which comes from some other place. That's all we need. If we can do that, we can do all of these operations with electrons that we've been talking about doing with water.
Right. Really important point. All that stuff holds up. Let's go get this one in here. The stuff about Boolean logic is super important, honestly.
Hi everyone. I spend a lot of time mashing away at a keyboard trying to tell the computer what I'd like it to do. Even my oddly shaped computer that constantly gets teased for looking like a trash can is unbelievably good at following instructions. Unfortunately,
And let me find out where it starts, because he's got this thing. Here it is.
if I close both of these switches, already this
So that's your and. This is and. So A and B have to be together for it to be completed.
is a kind of simple logic. We're testing if two conditions are true. Switch A is closed and switch B is closed. If we
Legit. So it's just going through here, going to this battery to the negative side, go up, up through here, back out the positive side. through this LED, which is just showing electricity flowing through, and then a couple very clever use of paper
We represent
clips.
an open switch with a 0 and a closed switch with a 1. These are the different configurations we could have. And here's the output. 0 meaning the light would be off, and 1 meaning it would be on. Since that's only the case when A and B are 1, this is known as the logical AND operation. And this kind of table, by the way, is called a truth table. Here's a bit of
Truth table. The Boolean truth. Yeah, it's a when they talk about truth table, it's like the Boolean, specifically in this category of Boolean math, not truth of the world. Math is always co-opting these general terms to mean very specific things and very, very specific domains. So that was someone that I had to kind of figure that out. I don't know if I really said that, and people don't tell you when they switch context between the general and this very specific. So a truth table.
a different circuit. This time we only have one switch, and even though it's open, the light is currently on. If I close the switch, now the light will go off, because we've created an easier path for the current to travel. So we're essentially inverting the input. If the state of the switch is 0, the output is 1, and vice versa.
That's a very inefficient use of not, but it definitely works, because this connection is going to get real hot. Because this is very inefficient. It's just going to drain that battery super fast because it's going as rapidly as possible. That's why it's bypassing here. Think of it like the water's rushing down here. It's like this takes a while to go up. This one's like boop down. It just goes. The water all is going to go down this way. Okay.
To travel. So we're essentially inverting the input. If the state of the switch is 0, the output is 1, and vice versa. And this is known as the logical NOT operation. Now, I've been controlling these switches with my fingers, which computers sadly lack. So in the very early days, electromagnets were used to open and close the switches, but this was kind of clunky and slow, so then came fancier technologies.
Yeah, this thing is called an electromagnet, and this is what opens and closes and runs motors and all that stuff. When you have a charge of electricity around a piece of iron, it electrifies it and makes it into a magnet, a temporary magnet, while the electric current is flowing, and as soon as it turns off, it's no longer a magnet.
Electromagnets were used to open and close the switches, but this was kind of clunky and slow, so then came fancier technologies like vacuum tubes, and finally transistors. As a tiny example of what transistors do, this is essentially that same NOT thing from before, just set up on a breadboard and with a transistor in the place of the paperclip switch. If we think of the current flowing in the circuit, it would look something like this. It can't flow through the transistor at the moment because right now it's acting as an open switch. But if we send power to the middle pin of the transistor, establishing a small flow of current like this, the fancy physics of the transistor will make it act like a closed switch instead, allowing the main current to flow through it like so. Just like before, the light is turned off because we've created a much easier path for the current to take. So essentially the transistor is a switch, which we can open and close with electricity instead of our fingers. I'd love to one day try and build a simple computer out of components like this, which is what Ben Eater has done in his very cool 8-bit breadboard computer series, but that's a little intimidating for me.
Yeah, we're gonna get into this one a little bit as we go along, so you can go listen to more of that. But that's the basic idea of the electrical stuff. So that's how we on-off switch. But how do we do the knot? So the knot, an efficient knot, not this crazy knot. So that knot that he was using does work, but it's not. You can't scale up. So they had to come up with something else with this, which was this electromagnet. And the big idea is an electrical current can cause a mechanical action. You saw him charge that little bolt. And then pick up all those paper clips. That's what this thing is doing. Instead of picking up paper clips, it's attracting this arm that throws this switch here. And this is what the schematic looks like. Here's the coil going around the magnet, or not around the magnet, going around a piece of iron. Basically, that's it. So you just have and this hooks up to a battery right here. So one side is this, goes up to this battery, and the other side goes to this side of the switch. Right, and the switch is then thrown that magnetizes this thing that pulls that armature, which is held open by a spring, and then this goes. Normally, this is a normally closed one. That's and so when the magnet here is magnetized, it pulls that handle over this arm, boop, and then makes that circuit go right here. This thing goes boop, and the circuit goes, and then this circuit. So that's when someone presses the switch here. That goes through the battery that energizes this relay, and the relay goes boop, and then in this case, this one says normally closed, but you can think of it. This one's it's normally open. Whoop. Normally open. I said before I clicked on it by accident, and then that will make a lamp go. So this is how a small energy source can power a large one. You can have lots of lamps and lights and all kinds of other devices running here. So that's basically the idea there. So let's go look at how make sure we understand how electromagnets put together.
Here we have an electrical wire with alligator clips, a battery, and a metal nail. How can we assemble these components to make an electromagnet that can attract some paper clips?
This has to be usually an iron-based nail. It can't be just aluminum. I don't know. It just makes sure it's iron. If you want to do this experiment, it's pretty fun.
Let's connect one end of the wire to the battery and wrap the wire around the nail. Now connect the other end of the wire to the other end of the battery. Cool, we've made an electromagnet. Test the electromagnet by moving it close to the paper clips. Nice, some of the paper clips are attracted to the nail. Disconnect a wire and the paper clips fall away. How can we increase the strength of the electromagnet so that it attracts more paper clips? Check the related videos to find out.
Yeah, so you can go explore that a little bit. And here's how you can look at when you record.
This is magnetic.
When you record, you can actually, with an electromagnet, you can actually induce in some other piece of iron or other magnetic material, you can actually make it stay magnetized after you pump it. After you put enough, when an electromagnet gets charged enough, it becomes like a permanent magnet. So it's always magnetized. So that's how this effect is working here.
It allows you to see where
So this film lets you see the field, which is important to see what the field looks like. When I was a kid, we didn't really have this. We didn't have the ability to see these fields. This is a new thing.
I'll show you how it works, along with some neat demonstrations. How does it work? Let's look at one of the ends of this magnet, the north or south pole, it doesn't matter which. Notice that we see the magnetic field as darker and brighter areas. Over the magnet's face, it's darker, but its edges are brighter. If we were looking at the magnetic viewing film under high magnification, we'd see that it's coated with many tiny, transparent microcapsules. Each capsule is filled with oil and a tiny flake of nickel. The nickel flake is thin in these directions and flat in these directions. In the magnetic field, the nickel flakes line up with their flat faces parallel with the magnetic field lines, like this, just like iron filings would. But notice here that the flat side of this nickel flake is facing you, and the light. The nickel flake is also shiny, so the flat side reflects light, and we see that as a bright spot on the viewer. Now look at the dark area over here. Again, the flakes line up parallel with the magnetic field, but that means the reflective flat sides are no longer facing the light. Instead, the thin edges are. And now we see a dark spot on the viewer. So the magnetic field lines are perpendicular to the viewing film where the film is darker, and they're parallel where the film is bright. You can do a lot of neat things with magnetic viewing film. Here's an old camera. Moving the film over it, we see a magnetic field here. The camera's speaker is in there. Most types of speakers contain magnets. Here's a magnet from an old hard disk drive. Notice that the face of the magnet has both a north and a south pole. And notice that we can't tell which is which. The magnetic viewing film doesn't help us with that. You've probably seen the demonstration where you drop a magnet down a metal tube, and the magnet falls slowly. If we put the magnetic viewing film over the tube, we can see where the induced magnetic field is, and therefore the magnet is. Notice the bright line.
That's pretty cool to see that effect. That's actually real. That's really what's going on. It's making these eddy currents that are slowing it down, which is what causes the magnets when they're to move and create electrical fields. So there's an electrical field and a magnetic field being created at the same time when that magnets are going through the copper tube.
Line that seems to be in the middle. Here's a stack of neodymium magnets on its own. Notice that from their side, there's the bright line across the middle of the stack. In fact, you can follow that brightness from one face all along to the other face. Remember, the brightness is where the film is most parallel to the magnetic field, so we're following it around the magnet. And here's how I erase it between tests, by waving this big stack of ceramic magnets near it. Here's a nail that I wrap some wire around to make an electromagnet. As I turn up the power supply, the electromagnetic field becomes strong enough to affect the magnetic viewer. And here's a larger electromagnet that I made. And again, we can see the field at the end. But also we can see that line on the side where the film is most parallel to the electromagnetic field. And you can also have fun with different configurations of magnets.
So feel like magnetic fields has a pole. It's got a north and a south, and it's polarized.
The boring old rectangular, the thing's more sinister looking.
We use that a lot in the computing. We use the heck out of that thing. That's pretty cool. All right, so that's kind of how that works, and we can also produce electricity. So an electrical field can move a magnet field can create electrical fields. So both back and forth. And I love these old movies because they actually show what's going on way better than the modern stuff. I'm surprised some of these modern guys just don't replicate it with more better looking stuff because it's so good. They're so good.
This represents a neutral atom in electrical balance. Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction. This movement of electrons in either direction constitutes an electric current flow. If we move the magnetic field more slowly across the wire, fewer electrons are affected in a given period of time, and the electric current flow is decreased. And when we stop moving the magnetic field, the electric current flow stops, and the electrons again move in all directions. If this wire is connected to a meter, we find there is no electric current flow. When the magnetic field is moved down, this meter shows current flow.
So all this meter has in it, I always ask, what's the meter have in it? It's just another magnet. And that's moving this needle back and forth, depending on the electrical flow coming through. It's basically a little motor.
In one direction. If the magnetic field is moved up, the meter shows current flow in the opposite direction. We can change the amount of electric current flow in several ways. Move the magnet faster, more current flows. Use a stronger magnetic field, still more current flows. Now coil the wire so that several turns are in the path of the field. Again, the current flow is increased.
This is how transformers work.
Stop moving the magnet, current flow stops.
You have multiple windings with one iron thing. Yeah, that's how it works. It's like change it from a electrical field to a magnetic field back to an electrical field. It's the same stuff over and over and over. Yeah, that's it. All righty. Let's look at this one. This one. I put these all here because this all super helps, like understanding how these things work, because it's really kind of interesting to see how they work. This one's got more about how
produces a magnetic field around the conductor.
Right. So this is a with the magnetic core.
Nothing more when dot current is fed for short.
Right here.
A bit represented a bistable.
So there was like those tiny little ferrite.
If the direction
cores,
of magnetism is reversed,
those were used to store data, store information.
the flux becomes negative,
They're going.
and the core holds a binary 0.
If the electromagnet, when it was polarized positive negative on one end versus the other, it'll make the core go one way. And if you reverse it, it goes negative and positive. It'll make the core polarize the other way. That's it. And they make them really small, so it doesn't really take so much voltage or current to change it from one to the other. And that's why they made it really teeny tiny.
Representing binary 1, and negative magnetic flux representing binary 0 may be reversed in some systems.
It's just saying sometimes it's a binary 1 is actually the negative to positive. Okay, you can pick, we can represent it one way or the other, but it has to be uniform throughout the whole system, or have some sort of interface that converts it. But you have to be, if you're going to pick one way or the other, pick one or the other. Don't use both.
So far, we've been establishing the function of magnetic cores. They store binary digits, or bits, 0 or 1. Now we're going to see how they do it, and also how they transfer bits from one core to another. To explain how cores store binary digits, we must know how they are constructed. Around the core is wrapped a conductor.
Oh, we saw that before. It's just an electromagnet. Okay.
Current flowing through the winding produces a magnetic field around the conductor.
So this is another property we're exploiting. One property is if you use it around a ferrite core, it'll pick stuff up. Another property is if you stick it on there long enough, it'll stay magnetized. That's the other thing we're using. This is what this is. This is the having it stay magnetized one and polarized one the way or the other. That's what we're exploiting here.
Because the core is made of highly permeable material, it forms a path for the magnetic lines of force. Because it is ring-shaped, the path it forms is a closed loop. The conductor here is wound so that current flowing in this direction produces a positive flux, setting the core in the binary 1 state. Current flowing in the opposite direction produces a negative flux, which sets the core in the binary 0 state. To show the polarity of the winding in a core diagram, we mark one side with a black dot.
Yeah, this representation kind of died out, but it's still useful to see how we did this.
By definition, current that flows into the winding from the dot side sets the core to 0. Current flowing into the non-dot side sets the core to binary 1. Remember, non-dot current for 1 and dot current for 0.
Okay.
Any winding around the
super
core
useful.
obeys the laws of electromagnetism. The magnetizing force it exerts is proportional to the amount of current flowing through it, measured in amperes, times the number of turns in the coil.
So this means like the more voltage and more current you put into the thing and the more turns it is, the more it's going to be stronger the field. Like
Or, as it is usually expressed,
magnetic field.
the ampere turns. Since the number of turns in this winding is constant, we can simplify the rule here. The magnetizing force exerted by the winding on the core is proportional to the winding's current. Suppose we increase the amount of current. Will the total magnetism of the core also increase?
It will, but not proportionately, as we'll see on this graph. We're going to take a minute and trace the magnetization curve of a core, because in this way we can point out some of the characteristics that make cores so useful.
So I will let you watch the rest of that. It is pretty interesting. This hysteresis thing, this hysteresis curve, why this happens this way, has to do with like how these cores get completely saturated in one way or the other from like from a neutral state to a saturated state, and how it comes back to a desaturated state, back to a polarized the other way. And it's like super interesting. But details that aren't necessarily that important right now. And then you can watch that another one on this core memory here. Very useful to know if the magnetic stuff is used all over computing. So, okay, I'm gonna get the vacuum tubes in the next video. I think this has gone on long enough.